Well, hello and welcome again to our journey into linear algebra. We've been looking at the Jordan form, or the Jordan blocks, and in the previous recording we defined a thing called a Jordan block, which is a slight generalization of a diagonal matrix, and it looks like this. You've got lambdas on the main diagonal, and you've got some ones on the off diagonal, and zeros everywhere else. And as with a diagonal matrix, the whole point about diagonal matrices is that you can take the nth power of a diagonal matrix very easily, and so we'd like to see how to get the nth power of a Jordan block. And the way we do this, we're going to split this up into two bits. So you can see from this, we can just take the matrix with the lambdas on the main diagonal, which is lambda times the identity, and then we take the bit that's left, which is just the ones down on the off diagonal, and that's this matrix, and we're going to call that n. Now if you play with some examples of this, if you look at a little 2 by 2 n matrix, if you took just 0, 1, 0, 0 and squared such a matrix, then you get the zero matrix. And in fact we'll see that by taking sufficiently large powers of n produces the zero matrix. And for this reason, this n is often referred to as a nilpotent matrix. It's a matrix whose eventually, take large enough powers, you get the zero matrix. So just as a little example of that, if we take J2 based on 5, so that means we've got a 5 on the main diagonal, and we've got a 1 up here, and then I can peel that off and write this as a separate matrix. So there's my 5i plus n. And if you take this matrix and square it, you'll discover that you get the zero matrix. Similarly, if we did this for a 3 by 3 matrix, then we'd end up with 2 ones off the main diagonal, but you find when you square this, it moves the 1 up into the next position, and if you cube it, you get the zero matrix. So what's happening in general here, if you take your nilpotent matrix, if you square it, it moves all the ones up one level in this minor diagonal. If you square it, if you cube it, then you move the ones up to the next level, and eventually they're going to disappear, and the nth power, or a certain power of the matrix, will be zero. Will give you the zero matrix. So in general, if n is a k by k nilpotent matrix, then n to the k will be the zero matrix. So what we'd like now to do, we want to exploit this idea to find the nth power of a Jordan matrix. Just as we found easily the nth power of a diagonal matrix, we want to find the nth power of a Jordan matrix. So to do that, we're going to write our Jordan matrix as lambda I plus n, and then raise that to the power n, and clearly this invites us to use the binomial theorem to do this. We've got to be very careful because we need the matrices in here to commute with each other to make the expansion simple, but of course lambda I is just a multiple of the identity matrix, which commutes with everything. So n and lambda I commute with each other, and so we can just expand this out in the usual way using the binomial theorem. So as an example, if we look at the case of where we've got a 4 by 4 Jordan block, so we've got lambdas on the main diagonal. It's a 4 by 4 Jordan block with ones floating above, and again I can write this as lambda I plus n to the power n, and I'm just going to expand this out then using the binomial theorem. So we get the nth power of the first term. Well, I to the n is just I. And then I'm going to get n choose 1 binomial coefficient. I get the n minus 1th power of this one, which gives me this, times I, multiplied by one of those, and I times n is n. The next term will be just n choose 2. We take the n minus 2th power of this one, multiplied by the second power of that one, which gives me this term, and then we do once more, we get n choose 3, n lambda to the n minus 3 n cubed, but because n to the 4th is the zero matrix, then the series stops at that point. There are no more terms in the series. All the matrices from here on are all zero. And I can put this now back, write this mess down in matrix form, and this is what you get. So just enjoy the form of this and the patterns here. So I've got a 4x4 matrix, 4x4 Jordan block, taking the nth power of it. And what it does is it gives you the nth power of the diagonal elements, nth power of the lambdas. In the off diagonal, I get n choose 1 lambda to the n minus 1, all the way along there. In the next off diagonal, I get n choose 2 lambda to the n minus 2. And in the final one up here, we get n choose 3 lambda to the n minus 3. Now clearly this is not as simple as taking the nth power of a diagonal matrix, but at least it can be done, and it's not that complicated, and also we see some lovely patterns happening in here. We see some nice patterns happening. So, as I mentioned here, it's not as simple as the diagonal case, but at least one can do it. It can be done. And just as a little example of that, we're going to find the nth power of a 3x3 Jordan block based on the number 2. So here's our Jordan block based on the number 2 of a 3x3 matrix. 2 along the main diagonal, 1's just floating on the off diagonal. So the nth power of that, pattern matching with what we just did a minute ago, you take the nth power of the main diagonal, you get n choose 1, now n choose 1 is just n, and you get the n minus 1th power of the 2, and that goes on the off diagonal. And the next one up here, you get n choose 2, which if you like, you can write as a half n minus 1, times 2 to the n minus 2. Again, it's not quite as simple as a diagonal nth power, but it's not too bad, and the patterns are nice and quite simple. And it is very nice we can actually do this. So, this brings us back now to the problem that we started with, and we're going to introduce this notion of a chain. So these Jordan blocks that we were looking at were, for a given matrix, were all predicated on the fact we had an n by n matrix with one sole eigenvalue lambda of algebraic multiplicity n, but it only gave you one eigenvector, so there was geometric multiplicity was only 1. Now of course this is not going to happen terribly often, but we'll worry about that a bit later. So this is a very, very special case. And we said we wanted a set of vectors v1 up to vn with these properties. So we wanted the v1, the first vector in my set, had to be an eigenvector. That means a v1 is lambda v1. The second vector, when you multiply it by a, it was almost an eigenvector. You got lambda v2, but you had an extra plus v1. So when you multiply a times v2, you get lambda v2 plus the vector just before it. And that was true all the way through the list. So you pick any vector, multiply it by a, you get lambda times that vector plus the vector just before it, all the way up to the last one. Now we didn't tell you how to get such a set of vectors. We just said that let's suppose that there were such a set of vectors, then we could put these into a P matrix, and we could get P inverse AP gives me this Jordan block. Now we're going to worry about how to actually construct this set of vectors here. And it turns out it's fairly easy. So to find such a set of vectors, which we're going to call a chain, we look at the general condition here on the vector vi. So these conditions here are equivalent to, firstly we need v1 to be an eigenvector. So v1 is an eigenvector, well that's easy to find. And if we look at this general case here, we can take this term on the other side, factor out the vi, putting in an identity matrix to make sense of it, and then a minus lambda I times vi is vi minus 1. That is, we can get from any of these vectors in the set to the one before it by multiplying by a minus lambda I. And this is true for I equals 2 up to n. So look what happens when we do the last one. So I do the same thing, I pull that term on the other side and factor it out, so I get a minus lambda I times Vn is Vn minus 1. I can now multiply both sides of this by a minus lambda I again, so I get a minus lambda I squared times Vn is a minus lambda I times Vn minus 1. But a times minus lambda I times Vn minus 1 gives me the vector just back 1. And you can repeat this process until you get to a minus lambda I to the n minus 1 Vn. And that will get you all the way back to V1. And finally, remember V1 is an eigenvector, so V1's in the kernel of a minus lambda I. So if I multiply by a minus lambda I for the last time, I get a minus lambda I to the n times Vn is the 0 vector, because V1 is an eigenvector, so it lives in the kernel of a minus lambda I. So when you multiply a minus lambda I times V1, you get the 0 vector. So that's because V1 is an eigenvector. Now just enjoy this last equation here. It tells me that this Vn is in the kernel of this matrix a minus lambda I to the n. When you multiply this by Vn, you get 0. So Vn belongs to the kernel of this matrix. Hence, we can, to find the vector Vn, which forms the end of the chain, we need to find a non-zero vector V in the kernel of a minus lambda I to the n, but we don't want it to be in the kernel of a minus lambda I to the n minus 1. It clearly will be, we can see from here, it clearly will be in the, well, it could well be in the, you could get a vector that's in the kernel of this one, but it's not the Vn that you want. So we take a vector V in the final kernel of a minus lambda I to the n, but not in the kernel of a minus lambda I to the n minus 1, and such a vector is called a generalised eigenvector. Having found this Vn, we can then construct the chain by just continually multiplying by a minus lambda I. That is, in terms of our list of vectors up here, we can get this one by looking in this kernel, and then we can construct all the others all the way back to V1 by simply multiplying by a minus lambda I. And that's going to give me the key to working out our Jordan form. Now we can represent this. I like using this thing called an onion diagram. Not sure it's used a lot in books and things, but I like the idea of the onion diagram. We'll see later it's quite a useful little analogy here. So we're looking at this innermost kernel here, this space, this set in here, this is the kernel of a minus lambda I. So that's the eigenspace. So if you will, this is the eigenspace of lambda of the matrix A. So that's the eigenspace in here. This one is the kernel of a minus lambda I squared, and that will this kernel will be contained inside that one, and we keep going all the way out, and this one's going to be this represents the kernel of a minus lambda I to the n. And what our V sub n that we're looking for, the last one, is going to be in this outermost kernel. Once we've got a vector here, we're going to chain our way back into the eigenspace by continually multiplying by a minus lambda I. Now, best seen at the moment with an example. We're going to do quite a few examples of this. So we have a matrix here, A, which is we have a matrix here A, which is minus 1, 1, minus 1, 0, 1, minus 4, 0, 1, minus 3, and we're told that this has only one eigenvalue, so it's got algebraic multiplicity 3, but geometric multiplicity only 1. So it's exactly the scenario we've been talking about. So we're going to work out everything, the Jordan form and the P matrix based on this matrix. Firstly, if we're told there's only one eigenvalue, then from the trace of this is -3. So 3 times lambda is -3, so lambda is -1. So there's our one eigenvalue for this matrix. And again, we just double check all the information. So the eigenspace, we add 1 to the main diagonal, gives me this, and the kernel of this one just consists of the vector 1, 0, 0. This has got rank 2, nullity 1, so it's got geometric multiplicity 1. There's only one eigenvector. Now, in order to build up our chain, I have to calculate, and there's no shortcuts here really, I have to calculate A plus I, that's this matrix here, and I've got to square it. So I did that by hand somewhere else, and that's what you get when you take this matrix and square it. You get this one. And this is now going to have rank 1, nullity 2. So there are 2 eigenvectors hiding in this kernel. Now we already know one of them, so I copy that one down. We already know one of them, so I may as well keep that one. And then I pick another one that's linearly independent with this one, but is also in the kernel of this matrix. And so if you take 0, 2, 1 will do the trick. Now, so just before I go to the next step, just in terms of the onion here, what we've done is, there's the innermost kernel, that's the kernel of A plus I. That's got one linearly independent eigenvector spanning that space. We go to the next kernel out, which is the kernel of A plus I squared, and we pick up another one. This is a generalized eigenvector. So this one here is what we're going to call a generalized eigenvector. It's a vector that is in one of these further kernels out. Now we need to go one more level, so we need to get the kernel of A plus I cubed. And you could take this and multiply it by that. You might like to take this one, multiply it by this one, to cube it. You can do that. But I just observe here that we're going to pick up an extra generalized eigenvector. So the kernel is going to be 3-dimensional. That means the nullity of this matrix is going to be 3. And that means its rank is 0. i.e. it's got to be the 0 matrix. If you don't believe me, you can cube it out and check for yourself, but you end up with the 0 matrix at this point. So I just need now to get my 3 generalized eigenvectors. So again, I'm going to keep the first 2. We already had these 2, so I'll keep these 2, and I just pick anything I like here, because it's got to be in the kernel of the 0 matrix, so I can pick anything I like here. And I generally go for 0, 0, 1 is generally a good one to pick. It's clearly linearly independent. It's got to be linearly independent with these 2, but this clearly is. So that's the vector here. That's my V in the outermost kernel. That's the Vn in the theory we've been looking at. Okay, now we've got to build our chain back into the center. So we now take our V in the outermost kernel. That's in the top kernel, but not in the one before. So that's my V is 0, 0, 1, and we build a chain. And the way I write it is like this. So there's our V. We multiply by A plus I. Now that's easy, because if we go back to here, multiplying this by 0, 0, 1 just pulls off the last column of this one. So that's going to give me this vector here. Now, by the way, that as we chain in, we're now in this space, and that was spanned by these 2 vectors, and so this one has to be in the span of those 2. And it's easy to check that it is. If you take -1 of these, -2 of those, you get this one. So that's a good way of checking. This vector has to be in the span. It's got to be in this kernel. It's got to be in the span of those 2 vectors. Now we chain into the eigenspace. So again, we multiply by A plus I. So again, you just got to do the math there and multiply it out, and you end up with minus 2, 0, 0, and that should have landed me in the eigenspace. So that's got to be a multiple of this vector. It's the eigenspace was the span of 1, 0, 0, and this vector is indeed in the eigenspace. It's just minus 2 times that vector. So again, it's another way of double checking everything works. If we take our chain in, that's what we get. Finally then, as we saw in the first video, we have to put these into the P matrix. Note the order. We put our eigenvector first, and then we write the chain down. So this is my V1, V2, V3. So note the order in which we write them down. And finally, the theory now guarantees that P inverse AP, what we've been doing, guarantees that P inverse AP is J, where J is a Jordan block based on the eigenvalue minus 1. There's the ones floating above, and that's a Jordan block of size 3 based on lambda equals minus 1. And we'll have a look at some further examples in the next video.